Hi everyone. In this video I'm going to kind of show you how to solve a system of linear equations by using the matrix formalism. We begin with our system of linear equations, in this case 2D, so two variables, an x variable and a y variable. Each of these expressions describes a line. When we're solving this system of linear equations, what we're essentially doing is we're looking for where do these two lines intersect. And they either intersect at a point, giving you a solution, or they intersect on a line. If they're the same line, they overlap everywhere, or they don't cross at all, which in 2D would mean that they're parallel lines. In 3D, there's other things that can happen. Anyways, we don't need to worry about that. We just need to follow a non-geometric process, an algebraic process, to solve the system of equations. We would begin by putting the SLE into matrix form, taking the coefficients in front of x and y and putting them into the coefficient matrix, and then putting the constants on the right-hand side and the augmented part of that matrix. Then, using magic, we would row reduce the matrix. Just kidding. We're not going to use magic. We're going to use elementary operations. Those same elementary operations we were talking about before, multiplying a row by a constant, or rather multiplying, so instead of multiplying an equation by a constant, we're multiplying the corresponding row by a constant. We can swap the order of two equations. But in matrix formalism, that would be swapping the order of two rows. And then last, we can replace one of the equations by itself, plus or minus a multiple of another equation. Well, we're going to do that with rows. We're going to say I can replace a row by itself, plus or minus a multiple of another row. Doing some sequence of those moves, we would get to this point. A matrix 1, 0, 0, 1 for the coefficient part, and then vertical line 1, 2. Once we get to this point, we can state what the solutions are. We would do this by running the process of SLE to matrix, running that backwards, matrix to SLE. First column represents the x variable, second column represents the y variable. So when we read row 1, it says that x, or 1 times x plus 0 times y is equal to 1, 0 times x plus 1 times y is equal to 2, which very clearly states that x is 1 and y is 2. That means that these two lines cross at that point, at the point 1, 2. So here's an example in R3. This matrix has been fully row reduced, so the hard part's been done. Now we have the final state, the final fully row reduced matrix. All the leading ones are there, they're all happy. And all we have to do is state what the solutions are. Row 1 says, it says that x is equal to 7. 1 times x plus 0 times y plus 0 times z is equal to 7, so x is 7. And it also tells us our variables are x, y, and z, so that's not any guesswork. Row 2 says that y is equal to 0. We have 0 times x plus 1 times y plus 0 times z is equal to 0. And row 3 says 0x plus 0y plus 1 times z is equal to 2. So our solution is x comma y comma z is equal to 7, 0, 2. If you're curious, the initial SLE, which this question didn't show us, would have been ax plus by plus cz is equal to 7, and then similar for the other two equations. Each of those is a plane. What we found is we found the point of intersection of three planes. Okay, here we have three equations, each corresponding to a hyperplane, because it's 4 variables. And we're asked for what the system, or I gave it away, but what the solution is. Where do these 4 hyperplanes intersect? So three hyperplanes intersect. There's 3 hyperplanes. 3 equations means 3 objects. We were given something with more horrible numbers. It's been simplified. This is what the simplified form looks like. It's been fully row reduced, and now we have an interpretation step. Again, we cannot simplify this one any further. How do we interpret the solutions? Cannot simplify further. Must interpret solutions. So that's kind of step one, row reduce. That's been done for us. It says, well, it doesn't actually corresponding RREF augmented matrix, so it does tell us it's been fully row reduced. Otherwise, do the RREF, do the reduced row echelon form thing using elementary operations, which we'll do next. Step two is any column without a leading one is a parameter column. We have to give it a label. I'm going to label column 3 with a T. I have a T there. So now what else? Let's look at the fourth column. Label column 4 with another letter. You could use S if you want. I'm not going to use S though. I'm going to use R because my 5s and my S's look the same. Now, read each non-zero row. So what does row 1 say? What does row 2 say? I'll put row 3, even though it's a 0 row, it says nothing. There's no useful information contained in row 3, but row 1 and 2 is containing useful information. Row 1 says the following. It says that x1 plus 0x2 plus 2 times x3 plus x4 is equal to 9. Now, forgot to label the R. Oh. When we label those columns, we're replacing the x3 with a T, we're replacing the x4 with an R. We're just saying we have complete freedom to pick any number we want for x3 and x4 for those two variables. However, that choice is then going to define what x1 and x2 are in terms of those variables. So there's an infinite number of solutions, but they're not random. We can't pick anything we want. We do have complete choice over the two parameters, T and R. That choice then prescribes what happens to x1. So what I'm going to do next is I'm going to rewrite x1 in terms of R and T. Just rearranging, bringing everything to the other side. So x1 is equal to everything else. So x1 is equal to 9 minus 2t minus r. I can do the same thing for row 2. Row 2 says that 0 times x1 plus 1 times x2 plus 1 times x3 plus 5 times x4 is equal to minus 5. So if I rewrite that one, also in terms of t and r, then I get that x2 is equal to minus 5 minus t minus 5r. Now I have an x3 and I have an x4, and all I do for those is I say what they are in terms of their label. x3 is equal to, I called it t, so x3 is t, x4 is r. And I can state our solution. Solution is x1, comma, x2, comma, x3, comma, x4 equals 9 minus 2t minus r, comma, minus 5 minus t minus 5r, comma, t, comma, r. I'm not going to ask you what this geometric object is, at least not right now, but think about it. If one parameter gives you a line, what do you think 2 parameters would give you? Okay, and then last. Okay, this says that, well, is it row reduced? We got leading 1 happy, leading 1 happy, leading 1 happy, so 3 happy leading 1s. They're happy because there's no non-zero numbers in their columns. They're the first non-zero numbers in their row. So it's fully row reduced. Do I let that 4th column equal t? Because there's no leading 1 inside that column. I could, but I don't have to. Why? Look at the last row. What does the last row say? This is a yay. No work needed. Look at row 4. It says that 0x1 plus 0x2 plus 0x3 plus 0x4 equals 8. That there's some combination of x1, x2, x3, and x4 that you could plug into that expression in the left-hand side and get 8 somehow. So 0 times something plus 0 times something else plus 0 times something else plus 0 times something else is equal to 8. This is impossible. You're multiplying all those pieces by 0. All you're ever going to get on the left-hand side is 0. This says that 0 is equal to 8. 0 equals 8 is impossible in the past, in the present, and in the future. So no solution. Original SLE must have been inconsistent. Okay, and that's it. So for this week, don't worry about row reducing in matrix format. Do some practice of elementary operations inside the SLE format before putting it into matrix. Work on the problems that are related to interpretation of what do the solutions look like? Is there no solution? Is there family? How do you rearrange the parameters? And that's it. See you next time.